Hi all, this is Dr. K. Raghuram Mohan Reddy, Associate Professor, Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. The course name is Unconventional Machining Process. The topic name is Material Addition Processes Part 1. This comes under Content Beyond the Syllabus for the Unconventional Machining Process. Right. At the end of this session, student will be able to understand the rapid prototyping fundamentals. This is the course learning outcome. Now, introduction to rapid prototyping. Rapid prototyping, in short, it is RP. So, in subsequent slides, if you find wherever RP, that is rapid prototyping. Okay, right. Rapid prototyping is a group of modern manufacturing technologies that are used to produce three-dimensional prototypes from CAD representations. Okay, so here rapid prototyping is a group of modern manufacturing technologies that are used to produce three-dimensional prototypes from CAD representations. What is CAD? Computer aided design. So the input for the rapid prototyping is that CAD, computer aided design. So we have to supply two-dimensional drawings to the or three-dimensional drawings to the RP setup. Right. These methods are generally similar to each other in that they add and bond materials in a layered fashion to form objects. Okay, right. Already we have discussed traditional manufacturing methods, unconventional manufacturing methods. In traditional manufacturing methods, what we are doing, we are subtracting the material from the workpiece. Even with unconventional machining also, what we are doing, we are subtracting but with sophisticated technologies to get high precision and to work on very hard and brittle materials. Okay, even to get intricate shapes also, we are using unconventional machining process. But here with rapid prototyping, we are not subtracting the material. In order to get the any part or component, we are adding material layer by layer. Okay, so this layer by layer technique is nothing but rapid prototyping. Okay, right. These techniques are also referred to as solid free form fabrication. Okay, SFF, solid free form fabrication. Okay, solid free form fabrication. In short, it is SFF. Okay, right. So in subsequent slides, if you find RP, that is rapid prototyping. Okay, right. Rapid prototyping uses physical and chemical processes similar to those used in non-traditional machining. These processes involve progressively adding materials. Okay, the non-traditional machining methods were discussed in previous chapters and are summarized in table 1. Let us look at here. Okay, chemical processes, thermal processes, liquid jet, solid jet, ultrasonic processes. So far we have discussed in the previous presentations. Okay, and material removal by chemical milling, electrochemical milling, laser beam machining, plasma beam machining, electron beam machining, electro discharge machining, water jet machining, abrasive jet machining, ultrasonic machining. Okay, so these are the phenomena, these are the various processes for the material removal. Okay, and correspondingly the material addition will be through stereolithography SLA, okay, photopolymerization, laser induced carbon vapor deposition CVD, okay, selective laser sintering, okay, plasma spraying, electron beam sintering, electro discharge deposition, 3D inkjet printing, powder jet laser cladding for these phenomena. Okay, so under chemical, stereolithography, photopolymerization, laser induced carbon vapor deposition, CVD. Okay, so these are chemical processes, whereas thermal processes are selective laser sintering, plasma spraying, electron beam sintering, electro discharge ED deposition. And under liquid jet, 3D inkjet printing. Okay, right. In unconventional machining process, the corresponding one is abrasive jet machining. Okay, sorry, water jet machining. In solid jet, abrasive jet machining, that is in RP, that is powder jet laser cladding. Okay, and there is no alternate for this ultrasonic processes in the rapid prototype. Right. Most rapid prototyping processes are still in pre-commercial stage. Okay, right. It uses a wide range of materials including paper, plastic, metals, and ceramics. Okay, right. Applications of RP include toys, aerospace, and advanced medicine. Okay, right. A key success factor of rapid prototyping is its ability to produce complex shapes. Okay, so RP is effective for materials that are difficult to machine using traditional methods like certain metals, ceramics, and composites. Okay, RP can create objects of various sizes from tiny to large structures. Okay, so with rapid prototyping, we can make even small screws or pins up to huge bridges. Okay, right. Advantages of rapid prototyping. Okay, builds complex three-dimensional geometrical shapes, uses a generic fabrication machine that does not require part specific tool, and requires a minimum of or no human intervention. Okay, next, produces accurate prototypes in a short time at a minimum cost. Okay, first one is builds complex three-dimensional geometrical shapes, uses generic fabrication machine that does not require part specific tool. Okay, right. Classification of RP techniques. RP means rapid prototyping. Okay, right. During 1991, Kruth classified the RP techniques according to the raw material used into liquid basic techniques, powder basic techniques, solid basic processes. Okay, some of these methods depend on solidifying a liquid polymer by the impact of light or laser, or by the curing of powders to create the prototype. Okay, other processes are based on melting, deposition, and resolidification of plastic or resin materials. Okay, right. Now, liquid based techniques. Okay, so here we have three types of techniques: liquid based techniques, powder based techniques, and solid based processes. Okay, already we have discussed that. Now under liquid based techniques we have these. Okay, so first one is stereolithography, holographic interference solidification, beam interference solidification, solid ground curing, liquid thermal polymerization, fused deposited modeling, multi-jet modeling, ballistic particles manufacturing, shape deposition manufacturing. Okay, right. Let me reiterate one more time. There are totally 9 liquid-based techniques. Okay, stereolithography. Okay, holographic interference solidification, solid ground curing. Third one, beam interference solidification. Fourth one, solid ground curing. Fifth one, liquid thermal polymerization. Sixth, fused deposition modeling. 7, multi-jet modeling. 8, ballistic particles manufacturing. 9, shape deposition manufacturing. Now let us discuss stereolithography in detail. Okay, so before we discuss stereolithography and all these things under liquid based techniques, now let us finish these things. Okay, so far we have discussed liquid based techniques. There are 9. Now let us see powder based techniques. Okay, what are the powder based techniques? Selective laser sintering, laser engineered net shaping, 3-dimensional printing. Okay, what are those? Selective laser sintering, laser engineered net shaping, 3-dimensional printing. Okay, now solid based techniques. Okay, 1, solid foil polymerization, laminated object modeling. Okay, solid foil polymerization, laminated object modeling. Okay, right. Now let us discuss stereolithography. Okay, stereolithography is the liquid based technique. Okay, so stereolithography is the liquid based technique. Okay, so in liquid based techniques 9 types are there. That the first one is stereolithography. Okay, right. Stereolithography, in short, it is SLA. Excuse me. Stereolithography is the most common rapid prototyping technique that employs layer by layer manufacturing based on polymerization. Okay, so here layer by layer manufacturing. Okay, based on polymerization. Okay, right. Here the medium is liquid. Okay, that's why it is liquid based techniques. So that liquid will have to solidify. Okay, so solidification happens by polymerization that results from the impact of a laser light on the upper surface of the liquid. Okay, right. So stereolithography is the most common RP technique, that is rapid prototyping technique, that employs layer by layer manufacturing based on polymerization. So here each layer should have to solidify. Okay, once the layer, excuse me, once the layer is formed, that layer will have to be solidified. Okay, right. Solidification happens by polymerization that results from the impact of a laser light on the upper surface of the liquid. Okay, right. Light polymerization of the liquid is limited to a layer thickness of a few tenths of millimeter below the surface. Okay. Now later we will see the setup. Okay. Now you understand few tenths of a millimeter. Okay. Light polymerization of the liquid is limited to a layer thickness of a few tenths of a millimeter below the surface. Okay. Illumination and hence polymerization of the surface liquid is restricted to pattern that corresponds to the parts cross section. Okay. So this illumination and polymerization subsequently of the surface liquid is restricted to a pattern that corresponds to the parts cross section. Okay. Right. Once the layer is completely traced, it is lowered by a small distance into the liquid and second layer is traced right on top of the first. Okay. So what will happen here? The layer, that means the liquid layer will be on top. Okay. And it will be solidified, so it will get down little so that another layer of liquid will come onto this surface. Again that layer will also solidify, again the table will move down, again another layer will come, that layer will have to solidify. So this is the layer by layer technique. Okay. Right. The self adhesive property of the material causes the layers to bond to one another and eventually form a complete three-dimensional object after many such layers are formed. So based on the thickness, required thickness, the number of layers and the different profiles of the layers will be fused, what is that called, adhesive and solidified. Okay, right. Some objects have overhangs or undercuts, which must be supported during the fabrication process by support structures. See, here, let us say our requirement is this one. Okay, so this is the base. Let us say it has started from here. But here at this end, we do not have anything. Suppose if we add layer by layer, what will happen? This will drop down. So in order to get this one in the design itself, so from this floor we have to give one support. So layer by layer this will also generate. So finally this portion will be supported, and at the same time after completion of the work we can remove this support. Okay. Right. These are either manually or automatically designed or fabricated, right, along with the object. So this is the required object. Okay. But here we are creating for the support. Okay. This should be light strength. Okay. Right. Upon completion of the fabrication process, the object is elevated from the liquid and supports are cut off. That's what we have discussed. Okay, upon completion of the fabrication process, the object is elevated from the liquid and the supports are cut off. Okay, right. SLA process. The following is the sequence of the SLA process. Okay, what is SLA? Selective laser. Sorry. Second one here. Stereolithography. Okay, SLA means stereolithography. So far we are in this only. Okay, not SLS, SLA, stereolithography. Sorry. The following is the sequence of the SLA process. The first one, slicing software reads the CAD model and cuts it into the thin slices that depend on the resolution of the mechanical movement of the RP system as well as on the part geometry. So first one is slicing. Okay, so it slices. Second one, the computer receives the output from the slicing software that controls the corresponding transitions and rotations of the mechanical components of the RP system. Okay, so we have to give the CAD model input. Let us say this one. Okay, so obviously its cross section is some rectangle. Okay, so first it will take the first slide as the rectangle. Okay, again another rectangle will form on this. Okay, again one more rectangle, again one more rectangle. So here this is just like a notebook. In the notebook there are different pages. If we keep one page on another page, again if we repeat that one, what will happen? Finally we will get the three-dimensional one. Okay, right, here also the same. Okay, right. Third one, the process chamber filled with the photosensitive liquid polymer as an elevator like platform that can be raised vertically or lowered. Okay, right. The laser beam scans the selected surface area of the photopolymer. It cues the scan patterns and produces a solid section. Okay, right. The platform is then lowered so that another shallow layer of the liquid polymer covers the previously cued layer. Already we have discussed. The sequence is repeated to produce the complete part geometry. Okay, so this is the setup. Okay, principles of stereolithography. Okay, look at this figure 1. Controlling the laser beam and the platform movements through the servo control system. Figure 1 can therefore produce a variety of parts. See here what will happen. See, this table is lowering. Okay, it is moving downwards in the Z direction. Step 1. Okay, so the top layer is solidifying. Okay, through the laser beam. Okay, again in step 2 what is happening? It is lowered down to little. Okay, so in the first instant this one over. Okay, in the first instant this one over. Okay, let us say in the first instant this one over. In the second instant this portion, why? Because it has lowered this much distance, so in the second instance that layer will be solidified. Subsequently, this is second, already we have decided, this is third, this is fourth. So here also same, the first layer will be cued. After that the ramp lower down so that the liquid layer occupies the previously cued layer, so that it will be cued then. Okay, so this operation will be repeating till the prototype completes. Okay, so here the mirror deflects as per the profile, that is slice of the CAD input. So based on the CAD input, here the mirror deflect the laser beam so that that laser beam moves in that path, so that it will fuse the corresponding profile space. Okay, otherwise every time it will move in the same line. So it has taken the input from the CAD. Okay, so from the CAD the slice will generate, so that slice will be the input to the profile of the latest layer every time of this process. Okay, every time one layer is curing. Okay, every time that layer we have to get from the slices. Okay, that's what we have discussed. Next, advantages and disadvantages of stereolithography. Okay, just advantages. Right, it has a high accuracy of plus or minus 0.1 mm and produces a good surface finish. It produces semi-transparent materials that can be processed for optical clarity. The process is fully automatic. can come to disadvantages, there is a limited range of materials that can be used. Okay, it has relatively high cost compared to the other RP methods. Working with liquids can be messy. Okay, so every time it has to uh, polymerize, but the thing is every time we will have the same liquid layer on the top. Okay, so some messy maybe. Okay, parts often require post curing operation. So already we have discussed that every time we have to post cure. Okay, maybe sometimes sand blasting or some other blastings, hard blastings are required in order to remove the any parts, or in order to remove the supports we have to do some other curing operations. So these are the references with this. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.